Hi, welcome back to Learning Chemistry with Reba. Today we can discuss the regeoselectivity aspect of Diels-Alder reaction. Before moving to the explanation of regeoselectivity given by Diels-Alder reaction, we have to first know what is regeoselectivity, what is regeoselectivity in a reaction. For that, here it is given an example. The attacking reagent here is NBS in 95% acetone. We know NBS in 95% acetone gives two reactive species. One is bromonium and Br plus, and the other is OH minus ion. And here the NBS is going to attack this carbon-carbon double bond of this reactor. The reaction can happen in two ways. That means one bromonium ion can attack either here or here. But only one position, one carbon center is preferred by the bromonium ion. That is regeoselective. It is selective to the region. So here we can see that in this reaction, the bromonium ion is selective to this carbon atom. That means the bromonium ion attacks here, preferably to get this product as a major product. Here we can see the bromonium ion attack here preferably, and thereby OH minus ion. When the bromonium ion attack here, the double bond is shifted to here, giving here negative charge and here positive charge, and to this positive charge the OH minus ion attack, and hence this is the major product. This why bromonium ion preferred this center for the attack means here the carbanion is formed here and here forms the carbocation. This carbocation is stabilized by this phenyl ring, and hence the attack of bromonium ion at this center is preferred attack, and here thereby there forms a regioselective product. This is the regioselective product. This is major, and this is the other product will be the minor. So the regioselective reaction means the attacking species prefers one region selectively to get the major product. So and now we can move to the regioselectivity given by the Diels-Alder reaction. Here it is given the Diels-Alder generalized representation for the Diels-Alder reaction. It is given a diene and a dienophile. The diene is butadiene and the dienophile is a simple ethene in thermal condition, giving a cyclo-added product, that is cyclohexane. To study the regioselectivity in the Diels-Alder reaction, we have to first know about the molecular orbital diagram. Here we can see that the molecular orbital diagram of butadiene, we already studied or discussed this molecular orbital diagram in the last video. Here we can see the butadiene. Again we can see here the butadiene has 4 molecular orbitals. We can see that butadiene has 4 pi electrons, 2 pi bonds and 4 pi electrons. These 2 pi bonds or 4 pi electrons are formed by the 4 p orbitals of these 4 carbon atom. P orbital of this and this and this. So there are 4 p orbitals. These 4 p atomic orbitals combines to get 4 molecular orbitals. We know as per Amour theory, the number of atomic orbitals will be equal to the number of molecular orbitals. Here we can see there are 4 atomic orbitals, and these atomic orbitals combine to get 4 molecular orbitals, and the molecular orbitals are psi1, psi2, psi3 and psi4. We can see psi1 is the lowest, then psi2. This is arranged according to the increasing energy, and we know that there are 4 pi electrons. Each molecular orbital accommodates only 2 electrons, and hence 2 electron enters the psi1 lowest energy molecular orbital, and the other 2, the remaining 2 accommodates here at psi2, and hence the HOMO of the diene is psi2 and the LUMO of the diene is psi3. This HOMO means highest occupied molecular orbital. This is the highest occupied molecular orbital, therefore psi2 forms the HOMO, and this is the lowest unoccupied molecular orbital, so psi3 forms the LUMO. Now we can see the molecular orbital, pi molecular orbital diagram for the simple alkene, that is ethane. We can see there is only one pi bond, hence there is one pi bond, and corresponding to that we have a pi star antibonding orbital, and we can see there is only 2 pi electrons. Each molecular orbital, since each molecular orbital accommodates 2 electrons, that 2 electron enters to this pi orbital and thereby forming HOMO, and this pi star becomes vacant and it forms LUMO. This is the highest occupied molecular orbital of ethene, and this is the lowest unoccupied molecular orbital for the ethene. And now we can see, we have already discussed that the interaction of a 4-pi component system and a 2-pi component system in Diels-Alder reaction takes place between the HOMO of the diene and the LUMO of the diene. We have already seen that. That means the electron enters from HOMO enters to the LUMO of the diene from the HOMO. That means the interaction in a Diels-Alder reaction takes place between the HOMO of diene and the LUMO of the diene. This is for simple. This is the case for the unsubstituted butadiene and unsubstituted alkene. And now we can see what happens with the substituted diene and substituted diene. Now here we can see a substituted diene. That is, here the diene is substituted by an alkyl group, that is electron releasing group, and the alkene, our ethene, is substituted using an electron withdrawing group. Here it is conjugated to an ester, and we are now seeing what happens to the molecular orbital diagram when the diene and the dienophile is substituted by using some electron releasing group and electron withdrawing group respectively. We can see that for a diene there are 4 molecular orbitals. There are 4 pi molecular orbitals for the diene, and when it is substituted with an electron releasing group, what happens? We can see the energy, the side 2 molecular orbital raises, get raised in its energy, and it comes to somewhat here. That means when an electron releasing group, when the electron releasing group donates its electron to this butadiene, we can see that the energy of the HOMO of the diene increases. And what happens when the dienophile is substituted with an electron withdrawing group? We can see that when it is substituted with an electron withdrawing group, the energy of the LUMO decreases. The energy of the pi star decreases, and somewhat comes to here. So, in conclusion, when an butadiene is substituted with an electron releasing group, the energy of the HOMO increases, and when the dienophile is substituted with an electron withdrawing group, the energy of the LUMO pi star get decreased. And now we can see that the energy separation between the HOMO and the diene will be less. HOMO and the diene will be less, and there will be interaction between the HOMO and diene, HOMO of the diene and the LUMO of the dienophile more readily than the unsubstituted diene and dienophile due to this small energy separation. We can see that the HOMO and the LUMO interacts more readily than the unsubstituted. That is why we have already said that the diene substituted with an electron releasing group and the dienophile substituted with an electron withdrawing group promotes Diels-Alder reaction. We have already seen the last video. Now we are moving to the further detail of regioselectivity given by the Diels-Alder reaction. For that, now we can see a simple alkene. This simple alkene has its LUMO like this. We have seen this in the last slide, that the LUMO is this pi star and it has one node. And we know that this is of high energy. LUMO pi star is at a high energy, and the coefficients of the both carbon atoms are same. We can see that coefficient means the electron density here. We can see that the coefficient, the corresponding electron density at this carbon and at this carbon atom is same, because it has same chemical environment here. Electronic chemical environment is same here. But when it comes to a substituted, when this alkene is substituted with an electron withdrawing group, we can see that this bond shifts to here and this bond shifts to here. That means their resonance is taking place. A conjugation is taking place. That means this pi bond shifts to here, and thereby this pi electron shifts to here. And we know that this is the alpha position corresponding to with respect to this electron withdrawing group, and this is the beta position. And what is happening when this alkane is substituted with this conjugating group? We can see now the LUMO will be like this. We can see that the beta carbon atom has the larger coefficient. Now the coefficient is unequal, and we know that the pi star orbital lowers in its energy. We have seen the last slide that the energy of the pi star get decreased when it is conjugated, and also there comes an unequal coefficient. That means here larger coefficient is seen in the beta carbon atom. We know that when this alkene is conjugated to this pi bond comes to here and this pi bond comes to here. That means here comes the positive center. Carbocation center comes here. This carbon becomes carbocation, and this part becomes higher in the coefficient. And now we can see this is the case for the diene. Now we can see the case for the diene. Here we can see a diene. This diene is made to react with the hydrogen bromide. And we can see in two ways the reaction can occur. First way, this carbon, this pi bond shifts to here, and this carbon becomes negative charge, and this attack hydrogen and the bromide ion is removed. That means this carbon is the reactive center now. In the other case, this will be the reactive center. That means this pi bond shifts to here, and there forms the carbanion, and that carbanion attacks this HBr. So for the case of diene, there is a chance for two reactive sites. One is a middle carbon atom, the other is the end carbon atom. See, if the middle carbon atom is undergoing the reaction, what happens? This bond shifts to here, and this carbon atom becomes negative, and this negative carbon atom attacks the HBr, and thereby this carbon atom, the end carbon atom, becomes positive charge. This is the first case when the attack is through the middle carbon atom. We can see the positive charge, the primary carbo. This is a primary carbocation. We know that this is a primary carbocation, and this carbocation is unstable. We know that primary carbocation is unstable, right? So this is not preferred. This is not a preferred attack. So the attack through this middle carbon atom is not preferred. And now we can consider this case. That means this double bond shifts to here, and this becomes the carbanion, the reactive center, and this carbanion attacks the HBr. That means attack at the end carbon atom. The attack is at the end carbon atom, and we can see that when this double bond shifts to here and when it attacks hydrogen, this carbon atom becomes the positive. And now this is a more stabilized carbocation because this is a secondary carbocation. And also this is an allyl carbocation. That means it has a resonance. When this is a carbocation, the pi bond can shift to here and the positive charge displaces to here. That means this carbocation is more stabilized, and thereby the attack at the end carbon atom is the more preferred one. So we can say that the diene prefers to be attacked is regeoselective to this carbon atom. And now we can see what happens. The home of butadiene. Home of butadiene is the molecular orbital, which is, we know that this is the molecular orbital which is going to get involved in the Diels-Alder reaction. We can see that for a HOMO of butadiene, normal cases without any substituent, we can see that what the coefficient will be lesser for the middle carbon atom and which will be greater for the end carbon atom, right? Here we can see the coefficient is greater for the end carbon atom because the reaction through the end carbon atom is more preferred than the middle carbon atom. The reaction through the middle carbon atom is not preferred. The reaction through the end carbon atom, let it be here or here, not the middle one. This is not the reaction site, but the end carbon atoms are the preferred ones. So the larger coefficients are seen with the end carbon atoms. But now we can look when the butadiene is substituted. When it becomes substituted, here we can see two substitutions by the alkyl group is seen, and now we can see there are two chances. One chance is that this double bond shifts to here, and there here becomes the carbanion center, and it attacks the HBr, and automatically this carbon atom becomes the positive charge carbocation. And we can see this is a more stabilized one because this is secondary carbocation. Also, it is stabilized by this double bond. This is an allyl carbocation. So this reaction is preferred, and this is the regioselective because regioselective at the end carbon atom. So because of the formula, why it is regioselective preferred center, because the carbocation formed is stabilized by the allyl group and also the secondary carbocation. And now this is the resonance structure, and this is a stabilized one. And now we can consider what happens if the attack occurs with this carbon atom like this. When this double bond shifts to here and this negative ion attacks here, we can see the carbocation is now formed here. This is now formed here, and we can see that when the resonance there is stabilization with allyl, but after the resonance this is the displaced carbocation. The carbocation is formed here. This is not a stable one. Even though this is stable one, the resonance stabilized, that means the other conjugated one is not stabilized. And when both of these are compared here, we can see that this is stabilized by the allyl cation also. After the conjugation, we can see the carbocation is formed here. This is the tertiary carbocation, hence this is more stable. But when it comes to here, after the conjugation, this is secondary one. After the conjugation, it becomes primary. This is unstable. So the preferred reactive site is at the end carbon atom. Here we can see this is the preferred reaction mechanism, and here the attack is through the end carbon atom. And now we can see what will be the coefficient of HOMO of this 1,1-dimethylbutadiene substitute butadiene. Since this is the reaction occurs through the end carbon atom, we can see the end carbon atom means this end. We can see that the coefficient of that end will be higher than the other three ones. So, but in conclusion, we can see the highest coefficient of LUMO in dienophile is seen at the beta carbon atom when conjugation happens. That means for a dienophile or a substitute to conjugated dienophile, the larger coefficient, the highest coefficient is seen at the beta carbon atom to the conjugating group, the respective conjugating. And for the diene, the highest coefficient is attained at the ends of the diene. It is attained at the ends of the diene, and the end is determined by the reactive mechanism. We have to look for the stable carbocation, and that end determines the highest coefficient in the case of diene. So now in this slide we have discussed what is coefficient and how a large coefficient is seen. For a Diels-Alder reaction, we can say that the Diels-Alder reaction occurs between the carbon centers of large coefficient, the highest coefficient carbon center of the dienophile and the highest coefficient carbon center of the butadiene interacts with each other. We can say for this 1,1-dimethylbutadiene, the highest coefficient is seen here. That we have seen the last slide, the highest coefficient is seen here for this 1,1-dimethylbutadiene, and the highest coefficient for the dienophile is seen at the beta carbon atom. For this dienophile, we can see the beta position alpha, then beta is here. So in Diels-Alder reaction, the largest coefficients interact with each other. So we can see this is the Diels-Alder reaction is going to happen here, and we can see the interaction comes between the largest coefficient. So when we write the concerted reaction, we can see this is the transition state. We have already seen the last video about the transition state, one of our video about the transition state coming between the in between the pericyclic reaction. We can see that when these when the diene and the dienophile interacts, there forms a transition state Even though this pericyclic reaction, Diels-Alder reaction, is a concerted reaction. What is concerted reaction? The simultaneous bond formation and bond breaking. Even though this is a concerted reaction, we can see the bond formation or is at first the bond formation occurs between these two centers, the largest coefficient centers. That means uh, this one and this one, the butadiene and dienophile at first get anchored at this position. That means after that only, after that not, but a little bit late for the other combination, other type of bonding between the butadiene and diene and dienophile. At first, the bond formation between the largest coefficient will be more enhanced than the other sigma bond formation. Here we can see the bond formation here is almost complete in the transition state, and here we can see that the bond formation between the sigma bond formation between the other two carbon centers is little. It's not complete as much as of this. So in short, we can say that in Diels-Alder reaction, the bond formation readily takes place, more readily, more effectively takes place between the carbon centers with the largest coefficients. So when these largest carbon centers of largest coefficient get anchored with each other, we can see that the diene and dienophile is now get anchored at a particular position, so that the position of this uh, two alkyl groups and the position of this ester group will not change. That means when this is anchored, automatically this bond is formed, followed by that, and thereby we can see that the two substituents comes like this in ortho-para relation, 1-2 relation. That means there is no other chance for any other relation, since the bond formation is taking place here between the largest coefficient more effectively and more readily. So this bond formation between the largest coefficient is just like anchoring the groups in their position, thereby resulting in a regioselective product. Here are some examples for this regeoselective reaction Diels-Alder. Here we can see the butadiene is now substituted with a methoxy group, and it is again made to react with the dienophile substituted with a cyanide group. So we are now looking for a reactant. Since this is a we know that Diels-Alder reaction is a pericyclic reaction, it forms only one product. So there is chance for the product formation of these two products, and we have to select one product, regioselected product, either this or this one. So how we can select, how we can find which is the regioselected product? For that, first we have to take a diene, and we have to look for the possible mechanism. Here in the case of diene, we know that methoxy group here has oxygen with a lone pair, and this lone pair is donated to this bond here, and automatically this double bond shifts to this carbon. And now what happens with the dienophile? We know that in the case of dienophile, this is a conjugate C double bond, and this is a conjugating group, and we know that beta position, that this position will be with the largest coefficient. That means this electron shifts to here and this shifts to here. So this is alpha position, this is beta position, and this position is have the largest coefficient, and in this case this carbon atom will have the largest coefficient. That means the the lone pair comes to here and this comes to here. So this is the carbon with the largest coefficient. This will not be the carbon with the largest coefficient. Look where the electron get accumulated. In the case of diene, the carbon where the electron get accumulated, that is the largest coefficient, and in the dienophile, where is the carbon which is deficient of electron, that is the largest coefficient. And next, Here we can see this is the methoxy group with the largest coefficient here. That means the lone pair comes to here and this comes to here. This is the largest coefficient. And for the dienophile, here is the largest coefficient alpha, beta. This is the largest coefficient in these two compounds. And we know that when these two compounds are in the transition state, the bond formation readily takes place between these two carbon atoms than these two carbon atoms, and thus when the sigma bond formation here takes place between these two carbon atoms, again the anchoring takes place. That this substituent and the substituent cannot move from its position, thereby correspondingly after this the sigma bond get formed here, and the product will be like this. We can see the substituent, then the electron releasing group of the diene and the electron withdrawing group of the dienophile is now in 1,4 relationship. So this is the major product, and this product will not be formed. So here we can see the major product. The major product in this reaction is a 1,2 related product, and the major product in this reaction is a 1,4 related product. So here this is an enol ether, E all ether. So when an enol ether is hydrolyzed, it readily undergoes hydrolysis to get a ketone. Is not important in this aspect. Here it is important. This is important. The regioselective reaction of the Diels-Alder. These are a reaction, very cyclic reaction. So we know that from these two examples, we know that 1,2 product can be formed and 1,4 product can be formed, but no examples are not yet seen with the 1,3 product. Here 1,2 and 1,4 products are only seen from these two examples. Now we can see. As a summary, we can say the regioselectivity. In a nutshell, we can see what is the regioselectivity for the Diels-Alder reaction. For a Diels-Alder reaction, the regioselectivity is that the electron releasing group in the butadiene and the electron withdrawing group in the dienophile should be either in 1,2 relation or should be in 1,4 relation. 1,3 relation will not be found. That is, in summary, we can say about the regioselectivity of the Diels-Alder reaction. In Diels-Alder reaction, the regioselectivity is that the electron releasing group of the diene and the electron withdrawing group of the dienophile should either be in 1,2 relation or in 1,4 relation. Either of these two products will only be formed as per the reaction mechanism or as per the largest coefficient in the orbitals of the diene as well as the dienes. So, electron releasing group and electron withdrawing group share ortho relation, that is 1,2 relation, or para relation, that is 1,4 relation. This is the regioselectivity for the Diels-Alder reaction in summary. Okay. And now we can see, we have already seen this example in the last video. Again, we can see there I have said about the regioselectivity, mentioned about the regioselectivity of this reaction. Now we can see what happens here. We can see this is a butadiene with a substituent, and this is a dienophile with a ketonic substitution. And we can see automatically, we can see there is 2 chance for the product formation. Here the diene and the dienophile reacts to get these two products. This can be this is a para related product, this is meta related product. We can see the para related product will be the major product. And in toluene, for first case we have used solvent toluene, and in 120 degrees in a sealed tube gets 71% of this para related product, that is the major product, and 29% of the meta related product. When we use this SnCl4 pentahydrate, that means if we use Lewis acid, we have already seen that when a Lewis acid is used in the Diels-Alder reaction, it increases the electron withdrawing capability of this ketonic group. It increases the electron withdrawing capacity of this group, and thereby the dienophile becomes more electron deficient, and this carbon atom beta carbon alpha beta, this beta carbon atom becomes largest in coefficient, and they interact with this carbon atom, and thereby leading to a more regioselective product. That means when this SnCl4 interacts with this CO group, the coefficient here become more larger than the other when in the case of toluene, and thereby increases the reactivity, and here since the coefficient increases, the bond formation between these two takes place more readily, and thereby giving a higher yield for the para-related product. And now we can see the Diels-Alder intramolecular Diels-Alder reaction. Here we can see a molecule, and the Diels-Alder reaction is taking place within the same molecule. And what is said that regioselectivity is found regardless of the position. When comes to a same molecule, when comes to the same molecule, we can't we can't adhere on to more regioselective aspects of Diels-Alder reaction, because uh, it is occurring in the same molecule and it has a perfect stereochemistry, and therefore it is unable to get adhere more into the regioselective aspects of Diels-Alder reaction. Here we can see this part of the molecule acts as diene and this acts as the dienophile, and we know that this is a portion with the largest coefficient for the dienophile. This is alpha and this is beta, so this is largest coefficient, and for the part of diene this is the largest coefficient, and the reaction, the bond formation takes place between the largest coefficient, and here the sigma bond is formed, and laterally the bonds, another sigma bond gets formed here. This is a Diels-Alder reaction to get a cyclohexane, and now we can say that these are the two. That means in the case of dienophile, this is the substituent, electron withdrawing substituent. Here comes the substituent, and for the diene, here comes the electron releasing substituent. And now we can see these two substituents, this one and this one, this one and this one. They are in they are sharing 1-2 relationship. In this case, it's okay. This is obeying the regioselectivity of the Diels-Alder reaction. This is okay, 1-2 relation, 1 and 2 relation. And now we can see another example. Here we can see that these two substances comes in 1-2 relation. And now we can see another example here. In this molecule, this is diene and this is dienophile. And we can see here alpha, beta. This position is a beta carbon atom with largest coefficient, and this is the position with the largest coefficient. But here it's not possible for the interaction between this largest coefficient carbon and this largest coefficient carbon. So here it is quite contrary to the what we have said in the last slides. Anyway, the 4+2 cycloaddition reaction occurs here without obeying the conditions for the Diels-Alder reaction. And then we can see this is the electron withdrawing group of the dienophile, and this is the electron releasing. This is the electron releasing group of the diene. This is the diene, and this is the diene, and it has the substituent, this one. And we can see that here is the substituent and here is CO2 is the substituent. Now these two substituents shares a 1-3 relationship. This is a 72% yield product, and here we can see this disobey the normal rules which we have concluded with the Diels-Alder reaction, regioselectivity in Diels-Alder reaction. So what is said that for the case of intramolecular Diels-Alder reaction, the regioselectivity is found regardless of the position of the conjugated carbonyl group. Okay, here we can see even though in normal case this is largest coefficient came here, and this is the reaction. So we can't say this is regardless. We can say this is regardless of the position of conjugating carbonyl group in the case of intramolecular disorder reaction. When it comes to the other disorder, intermolecular disorder reaction, strictly they obey the rule of 1,2 and 1,4 ortho and para relationship between the electron releasing group of the butadiene and the electron withdrawing group of the diene. But it is different with the intramolecular disorder reaction. Hope you all enjoyed the video and understand the matters of regioselectivity in disorder reaction. Thank you.